And we are back. This is lesson 10, talking about rational numbers and equivalent fractions. Here's your two objectives: identify sets of numbers and compare and reduce fractions. So let's go ahead and get rocking and rolling with them. Your fun fact of the day, quick, is that the average person laughs 13 times a day. Must be in Mr. Ayers' class. You get a lot of those in. 13 is a lot of times. All right, and let's go ahead and get on moving with the examples. Okay, first thing, before we can do any examples, we have to know these four terms: counting numbers, whole numbers, integers, and rational numbers. So again, we talked about this before. Counting numbers are the numbers that when you were 3, 4, maybe for some of you were 9 and you learned how to count, that you learned, okay? So we start with 1 and 2 and 3 and 4 and we keep on going, okay? Whole numbers are all of those counting numbers plus the number 0. So we go with 0, 1, 2, 3, and 4. Okay? Integers. Integers are all of these numbers right here, all the whole numbers, and then the opposites of the positive ones. Okay? So I'm talking, we can continue in this pattern the negative side, so I'm going to put a dot, dot, dot there. And then that's negative 4, negative 3, negative 2, negative 1, 0. Then all those positives again, 3 and 4. And then that pattern continues. Notice we got dot, dot, dots on both sides, ellipse on both sides, because it continues in both directions. So integers, again, are 0 and all the positive counting numbers, and then their opposites, the negatives. Okay, rational numbers. Rational numbers are anything that can be written as a fraction, okay, or some decimal numbers. Okay, so rational numbers, again, are all of these numbers. So we're talking again, so let's do like negative 1, 0, and 1, and those patterns continue with all those numbers we already learned for rational numbers. But then now we're including fractions, so 3/4. Okay, maybe we've got negative 5/7. Maybe we've got 10 over 3. Or sorry, let's go, 10 over 3. Okay, fractions like that. They could also be decimals, and they are decimals that stop, okay, or repeating decimals. So I'm talking like 1.5, 0.2, negative 1.34. Okay, maybe it is 3.3 repeating. Okay, those are all examples of rational numbers. So again, rational numbers are 0, all the positives, and all the negatives, and then anything fractions, positive or negative, and decimals that stop or repeat. Okay, so 1.5, 0.2, negative 1.34, 3.3 repeating. Pi would not be included because pi is a decimal that goes on and on forever but never repeats. Okay, so that would not be a rational number. We will talk about those kind later. Okay, so there's your examples. Make sure you have those in your notes because you'll want to know what all those words mean. Okay, we're going to example 1. Example 1 says describe each number in A through C as a whole number, an integer, or a rational number. Write every term that applies, then sketch a number line and graph each number. Okay, so for part A. Well, negative 3, we'll just go down the list, okay? Is negative 3 a whole number? Well, remember, whole number was 0 and a bunch of positives, so negative 3 is not a whole number, okay? But it is an integer, so it is an integer, okay? And it is a rational number, because rational numbers, again, are almost everything, okay? Rational numbers are almost everything. They are positives and negatives. They are fractions and decimals that don't repeat, or sorry, decimals that do repeat, and decimals that stop. Okay? But again, whole numbers are examples of rational numbers as well. So negative 3 is an integer, is also rational. And then we want to sketch a number line and graph the number. So I'm just going to go ahead and sketch a quick number line. We'll put 0 right here. 1, 2, 3. And negative 1, negative 2, negative 3, and put a dot on it. There you go. Alright, so B. Positive 2. Well, remember, we want to know, is it a whole number? Well, whole numbers are 0 in all the counting numbers, which 2 applies to, so it's a whole number. Every whole number is an integer, so we put integer as well. And every integer is a rational number, so it's also rational, so we have to put all 3 down. Again, we're going to sketch it on a number line. So here's 0, 1, 2. And I'm going to go ahead and put the numbers on the other side of it. So here's -1 and -2. And then letter C, 3/4. Well, 3/4 is not a whole number because it's not 0, 1, 2, 3, so on. It's not an integer. Okay. In fact, fractions, the only thing fractions are is rational. Okay, fractions are rational numbers. Now, when I sketch this on a number line, there's a few ways to do this. Here's how I like to do it, because I like to show I understand where 3/4 is. Okay, so I'm just going to put 0 and maybe 1 and maybe 2, and we'll put some negatives here. Well, 3/4 is part of the way in between 0 and 1, and we should show that we understand 3/4 is closer to 1 than it is to 0. So I'm going to put it kind of over here, okay? In between 0 and 1, but closer to 1. Okay, so there's 3/4. Now, if you ever graph a number that's not included in your number line, you should always write above it what it is. So that's 3/4 right there. Okay, so there you go. Remember, we have to write every kind of number that applies. If they're asking you, again, right here it says write every term that applies. Alright, let's go ahead and keep on moving on. Okay, example 2 says using prime factorization reduce 72 over 108. Okay, so we want to reduce the fraction 72 over 108. We want to figure out what is that equal to. Now, I'm going to stop here because the method specifically said use prime factorization. Okay, that's not an option for this one. We're not just going to divide each one by 2 until we get to the answer, or however you want to reduce it. We're going to learn this new method and use it. Okay, so prime factorization is just when you use a factor tree or downward division to break down a number. So I'm going to break down 72. Oh, let's go ahead and use a factor tree for 72. Well, I know that's 8 times 9. Neither one of those is prime. 8 breaks down into 2 times 4. 2 is prime, but 4 is not. Make sure that's a 4. Okay, 4 breaks down into 2 times 2. And those are both prime. And we also know 9 breaks down into 3 and 3, which are both prime. So now what I'm going to do is on the top of this fraction here, I'm going to write down all these prime factors in order from least to greatest. So I'm going to put 2 times 2 times 2 times 3 times 3, because that was all the prime factors of 72. 2 times 2 times 2 times 3 times 3. Okay, I'm going to do the same thing for 108. I'm going to break down 108. Oh, for this one, let's go ahead and use a downward division. I know 2 goes into 108. Again, I'm picking the lowest prime number that goes in. 2 goes into 108, and if I divide that, that's 54. If I divide 54 by 2, I get 27. Okay, 2 does not go into 27, so the next lowest prime number is 3, and 3 goes in there, and it goes in 9 times. Okay, and then we can divide 9 by 3 and get 3. Since this number is prime, I'm done. And all of these numbers are the prime ones that should be written for 108. So I'm going to put 2 times 2 times 3 times 3 times 3. And here's the nice thing about reducing a fraction with this is, what do we know about fractions? When we got the same thing on top and bottom, if they're multiplied, okay, we can simplify those. We can cross them out. Since all these are multiplied, I can simplify every single number that's the same. So like these 2's cross out. These 2's cross out. Okay, this 2 has nothing to cross out with, but these 3's can cross out, and these 3's can cross out. Now I could have also canceled, these 3's right here and these 3's. That's fine, as long as they match up with the same number. But the reason why I did it this way is because they were right below each other. Look at all that's left. It's 2 over 3. So there's the answer, 2/3. Okay, now you might be thinking, well, Mr. Ayers, that took a long time. It does the first time. The first couple times you're learning, this method takes a long time. However, once you get it down, okay, this method actually goes pretty fast, and it's a pretty efficient way to reduce fractions. Now let's say I would have had on top like 2 times 3 over 3 times 3. So let's say, this is a side note again, this isn't part of this number. Let's say I got things that look like this. 2 times 3 times 3, and on the bottom I got 2 times 2 times 3. Okay, times 3 again. Let's just do that. Okay, if these canceled out, and then these canceled out, well, look what's left on top. I just have 3. But on the bottom, I've got 2 times 3. Okay, which would be 6. And whoops, Mr. Ayers actually messed that up. Okay, but let's say I did end with that. 2 times 3 is 6. So I would have to write 6 down here. I'm looking going, well, this isn't reduced. Okay, so what did I forget to do? I forgot to cross these two out. So again, we would finish reducing this. 3 over 6 is 1/2. Okay? Now, but again, if this happened where you had two numbers on the bottom, you would multiply them together. But watch this. If I reduce these and cross this out, there's nothing left on top. If there's nothing left on top, you put a 1. And then on the bottom of this, there's 2. So if nothing is left on top or on bottom, you replace it with a 1. Okay? So that's kind of how we go about that. And let's go ahead and go to the last. Okay, and here we are in example 3 and example 4. Example 3 says, right, a fraction equivalent to 1/2 that has a denominator of 100. So, again, equivalent means equal to. So we want a fraction that's equal to 1/2 that has a denominator of 100. Well, denominator of 100 means a bottom number. So all we're doing is trying to fill in the missing numerator here. Since this is a numerator, I'm going to put n. Okay, well, this is a proportion. We learned how to solve these before. Okay, so 1/2 is equal to what over 100? Well, I know that this times 50 is 100, so this times 50 should be 50. Notice though, 50 isn't the answer. 50, they said write a fraction equivalent to that. So I've got to write it as 50 over 100. So here is a fraction equivalent to 1/2 that has a denominator of 100. Notice my answer is not just 50. It's actually writing the fraction with a denominator of 100. And the last one is compare 2/3 to 3/5. Just so it's a little bigger, I'm going to go ahead and do this. Okay, there's many ways to compare these. One way is to find a common denominator of each one and then compare them. Okay, there's another quick way you can use. Okay, here's one way that you can always use to compare two fractions. You can take the numerator of one times the denominator of the other. 2 times 5 is 10, and you write that over the numerator. So 2 times 5 is 10. Now, you can do it the other way too. 3 times 3 is 9. So again, I wrote that over the numerator I circled. Now you just compare these two numbers, 10 and 9. Well, that compares this way, it's greater than. Okay? So greater than. This method always works to compare two fractions. You take the numerator of one times the denominator of the other, and that gets 10. And the numerator of this one times the denominator of this one gets 9. And then you compare those two numbers. Okay, and the reason why that works I won't go into right now. If you have a question you can ask about it, but it has to do with finding common denominators is why that works. Alright, the whole entire lesson, so if you have any questions, make sure you ask. This is kind of what I feel like my slides are sometimes here with a bunch of information written down. So if you have any questions, make sure you ask them. Otherwise, happy homeworking.